my Department of Mathematics, State Indian University. I would like to start today about the lines in solid geometry. So first of all, we should know what is a line. A line, it is defined as intersection of two different planes. So let me illustrate the lines by taking two geometrical figures as shown on the board. So for the convenience sake, I would like to take two different planes. We have just now defined what is a line. A line is a geometrical surface obtained by the intersection of two different planes. So let us take two different planes as phi1 and phi2, which are denoted by the below equations. So let phi1 and phi2 be the two different planes. And phi1 is defined as a1x plus b1y plus c1z plus b1, and phi2 is defined as a2x plus b2y plus c2z plus b2. These two are two different planes. Now I would like to represent these two different planes geometrically as follows. So this is taken as phi1 and this is taken as phi2. These are two different planes. Now I would like to intersect these two planes. So the intersection part of these two planes is represented as follows here. So please here, this is first plane, and again this is second plane. So this is phi1, this is phi2, and the common portion which was obtained by the intersection of these two planes is represented with this dark line. So this dark line geometrically represents our line. So a line is defined as the intersection of two different planes. So the first form of the line is defined as phi1 is equal to a1x plus b1y plus c1z plus b1, and phi2 is equal to a2x plus b2y plus c2z plus d2. These two forms, they are called as asymmetrical form of the lines. Now when you speak about the symmetrical form of the lines, it is customary to study all the different forms of the lines that exist for a line. So apart from the symmetrical form, of course we have studied what is this asymmetrical form. Now we go for studying what is the symmetrical form. What is the symmetrical form of the line, and how, and what is the two-point form of the line, and what is the parametric form of the line. These are the different types of equations of lines that we use in our regular practice. So first of all, once the symmetrical form of a line is known, automatically two-point form and parametric form of the lines will be automatically calculated. So first of all, I would like to derive a small mathematical derivation which shows how a symmetrical form of a line can be obtained. For that, we draw a three-dimensional figure. A three-dimensional figure, as you know that the name itself indicates, it contains x-axis, y-axis and z-axis, and of course my area of projection will be on xy plane. Now of course when we generalize the idea to yz plane as well as the zx plane. So we start our discussion by considering a three-dimensional plane as shown below. So I would like to draw here a three-dimensional plane like this. This is x-axis, this is y-axis, and this is z-axis, and of course the intersection point is taken as origin. Now here, when I have taken this x, y, z plane, I have just defined a line as a intersection of two different planes. Therefore, I would like to draw one line on this xz plane. This is the line L. And I would like to obtain the equation of this line L in the symmetrical form of a line. So please here, for that, what I want to do here is, I would like to take two different points on the given line here. Let A and B be two different points which are separated by a distance r units. Okay, now I would like to take the coordinates of A as x1, y1, z1 and the coordinates of B as x, y and z. And the distance between the 2 points A and B is taken as r units. Now here what I would like to do now here is I would like to draw two perpendicular lines from the 2 points A and B on x-axis. So please here from A I am drawing one perpendicular line to x-axis and from B also I am drawing one perpendicular line to x-axis. Let us assume that these two perpendicular lines meets the 2 point x-axis at the 2 points C and D. Therefore, as you know that in the principle of identification of a coordinates of a point in any axis, the distance between O and C is defined as x1 because the coordinates of A is x1, y1, z1. Similarly, the distance between the O and D is taken as x units because the coordinates of B is x, y, z. From geometry, I can say that since OC plus CD is equal to OD, OC is x here and of course OC is x1, CD we have to calculate and OD is equal to x. Therefore, CD value becomes x minus x1. So, CD is equal to x minus x1. Now, again I would like to do a small manipulation. From the point A, I would like to draw a perpendicular line to B. So, draw a line perpendicular to B. So, draw a line from A to B. Therefore, this line A, perpendicular line, meets BD at E. Now, if you observe this figure, the figure AEB, it is called as a right angle triangle where angle AEB is equal to 90 degrees. Therefore, from the figure AEB is a right angle triangle and angle AEB is equal to 90 degrees. Therefore, from the right angle triangle I can say that A indicates what is called as A indicates the adjacent side, B indicates the opposite side and AB indicates the hypotenuse. Also, from the figure we can say that ACDE represents a rectangle Therefore, in a rectangle, the common property is opposite sides will be equal. Therefore, length will be equal, breadth will be equal, but length is not equal to breadth. But for a square, all sides will be equal. Therefore, AE is equal to CD. But we have obtained CD as x minus x1. Therefore, AE becomes x minus x. Therefore, AE value is taken as x minus x. Now, we assume that the angle EAB is equal to alpha. So, angle BAE is equal to alpha. Therefore, cos alpha is defined as adjacent side by hypotenuse. So, what is this adjacent side here? AE is the adjacent side. Therefore, this becomes AE and hypotenuse is AB. Therefore, cos alpha is equal to AE by AB. Now, cos alpha can be written as what is AE? X minus x1. And what is AB here? The distance between A and B is R. Therefore, x minus x1 by r is equal to cos alpha. We have defined in the very introduction, we learned that the cos alpha, cos beta, cos gamma, they are called as direction cosines, and cos alpha is defined as L, cos beta is denoted by M, and cos gamma is denoted by M. Therefore, I can say that I can replace cos alpha as L is equal to x minus x1 by r. Therefore, I can write this one as x minus x1 by L is equal to r. This is the value of r with respect to the x-axis. Similarly, if we consider the other projections with respect to y and z-axis, we get here. Similarly, we get y minus y1 by m. This is equal to r, and also z minus z1 by m is equal to r. Therefore, I can say that x minus x1 by L is equal to y minus y1 by m is equal to z minus z1 by m. This is equal to r, and this form it is called as the symmetrical form of the equation of the line. So we have studied two different forms of the line so far. One is called as asymmetrical form, which is not in a proper sense, which is not in the form of the equation of a plane, and also we have obtained the equation of a line in symmetric form. This symmetric form of a line plays a very vital role in the remaining part when studying the remaining parts of the line chapter, because every form will be in the form of symmetric form, and sometimes situation may arise. It may be possible to convert the asymmetrical form of a line into a symmetrical form of a line. But for the present situation, the symmetrical form of a line is a valid one. So here, this x minus x1 by L is equal to y minus y1 by M is equal to z minus z1 by M is equal to r. It is called as symmetrical form of a line. Similarly, using symmetrical form, I can obtain the other form of the line called as parametric form of the line. So what is this parametric form here? I will like to equate the individual terms. X minus x1 by L is equal to r. Therefore, x minus x1 is equal to LR. Hence, x is equal to x1 plus LR. Similarly, y minus y1 by M is equal to r. Therefore, y minus y1 is equal to mr, and hence y is equal to y1 plus mr. Likewise, I can show that z minus z1 by M is equal to r. Therefore, z minus z1 is equal to mr, and hence z is equal to z1 plus mr. Therefore, x1 plus lr, y1 plus mr, z1 plus mr, this form it is called as the parametric form of the equation of the line. So, three different forms are known. Now, I would like to end this class by telling the fourth different form called as the two-point form of this line. So, what is this two-point form? So, what is this two-point form? The name itself indicates it will be consisting of two different points. Once 2 points are given, it is possible to find the equation of a line using these 2 points, and the form obtained is called as the two-point form of the line. So here I would like to define the fourth form called as the two-point form. Just I will write for this one. So here let us suppose that fourth one, two-point form of the line. So what is this two-point form? So let us suppose that let the x1 y1 z1 and x2 y2 z2 be two different points. Therefore, using these 2 points, I can calculate the direction ratios. Therefore, the direction ratios of the given line is x2 minus x1, y2 minus y1, and z2 minus z1. These are the direction ratios of the given line. So, if I want to find the equation of the line in symmetric form here, therefore, x1, y1, z1, x2, y2, z2 are the 2 points. Hence, it becomes the two-point form becomes x minus x1 by x2 minus x1 is equal to y minus y1 by y2 minus y1 is equal to z minus z1 Z1 by Z2 minus Z1. This is this form. It is very much familiar with the form which we have studied in our 10 plus 2 classes. There you will be studying the 2-point form as x minus x1 by x2 minus x1 equal to y minus y1 by y2 minus y1. Because in our 10 plus 2 classes we will be limiting ourselves to studying 2-dimensional axis only. X-axis and y-axis will be taken into consideration. But here, as the line is a geometrical surface obtained in 3 dimensions, therefore 3 coordinates are taken into consideration. Hence, the equation of the line becomes x minus x1 by x2 minus x1 equal to y minus y1 by y minus y1 equal to z minus z1 by z2 minus x1. The line is passing to the point x1 y1 z1. Similarly, if the line passes to the point x2 y2 z2, then the equation of the line becomes x minus x2 by x2 minus x1 equal to y minus y2 by y2 minus y1 is equal to z minus z2 by z2 minus z1. So these two forms, they are called as the 2-point forms of the equation of the line. So in this today's lecture, I have defined the various forms of the equations of the line. Thank you.